to thank the organizers for the invitation to be here. And we are going to talk about Lorenz attractors. And firstly, these objects appeared when Edward Lorenz in 1963 was studying a model for weather forecasting. And to do this, he truncated the Navier-Stokes equations, like this, to this system. And for the first time, he saw some kind of phenomena that was not usual, not yet classified. And it was something like this, as being an attractor, and having a singularity in the origin, and displaying sensitive dependence on initial conditions. It's important to consider that the context of the time, it was a time when people was considering the possibility of describing all the systems through XMA models, something like that, and this was clearly an obstruction. And anyway, it was a numerical experiment. So in 1979, Guggenheim and Williams proposed this geometric model that somehow was the same thing that was in the Lorenz object. So it was a model with a singularity in the origin, having the two unstable manifolds like this here and this other one, and a stable manifold like here, with the feature that for z equal to 1, you can take a square here, and the dynamics here is like this. Half of this square will come here in this way until it reaches here this triangle, this yellow triangle, and it returns in this way with the tip in this position. And you have here foliations, okay, that are mapped into foliations via a strong contraction. So with this kind of model that was displaying the same main characteristics that the numerical experiment of Lorenz was displaying, they came to this Poincaré map of the square, okay? And this, because of the strong contraction of the leaves, induces a one-dimensional map like this here. And this, because of this condition on the eigenvalues, they have the expanding case, and they studied this, okay? The condition is on this and this here. They have to sum to be greater than 0, and they had the expanding case. So they studied these systems, and it was very easy to say a lot of things about them. But later, Arnaud Collet and Tressé in 81 studied the other case when this is less than 0. And the induced map looks like something like this here. Okay, so the situation is a little bit different. It's more rich, what can happen. And so after this, we can begin to consider what can happen in terms of attractors for such a system, okay? So we were going to speak about attractors, in which context we have the definition of attractor as in Milner's sense. We have that the basin of attractor of a set is a set of points whose future orbits accumulate in it, okay, like this. And when we define the basin of attractor of something, we can say, we can look for the a basin that that's relevant in terms of, in a topological sense, okay? That is, an attractor is a transitive compact set is a topological attractor. If this basin is relevant in the topological sense, that is, it's residual in an open set. And the same way we define a metric attractor as being one that has a relevant basin, okay, in the metrical sense. So what we are going to study now is the topological attractors that can occur for Lorenz maps. Something that we will take as hypothesis soon is that the induced maps have negative Schwarzian derivative. This is usual object that has good properties. It's defined like this, and we'll take maps with where this is less than 0. So I have to say that, okay, we are going to study to try to describe the topological attractors that can occur for Lorenz maps. So we can think a little bit what happened for things that we already know the classifications. As for example, the unimodal maps, like this here, if you have a negative Schwarz derivative and it's non-flat, okay, it means that it looks like a polynomial here near the critical point. And Guggenheim in '79, he classified the topological attractors that can occur for such a kind of map. And he got that it can only be a periodic orbit, an attraction periodic orbit, a solenoid, or a cycle of intervals. But to do this, he used Milnor-Thomson theorem, okay, to have a semi-conjugated conjugation with a affine map with inclination. Oops. And he used Milnor-Thomson theorem to make a conjugation, but here we do not have this theorem because we are going to work with the discontinuous maps, okay? So the context is different. We will no longer have the Milnor-Thomson theorem. And, okay, let's see other types of classifications they had in the 80s and 90s. So Bloch-Liouvitch in '89 and '91, they had a series of papers where they proved that the magical attractors can be of only one of these types, okay? So there is a fourth type here, perhaps, but with an additional hypothesis. Liouvitch has shown in '94 that the classification is the same as in Guggenheim classification for metrical attractors, the same way as in the topological attractors. So, of course, we kind of can use this as guidelines to think about what can happen in terms of topological attractors for Lorenz maps. Why? Because, for example, if we think that if you have a quadratic simple family, like this here, and think about the symmetric Lorenz here, okay? You just cut this and twist the right side, having this. You can see that the points, they are, when you iterate the function, they are at the same distance to the critical point. Okay, so their absolute values are the same. If we iterate a lot, they will look different, but indeed they will be the same. That means we have a semi-conjugacy 2-to-1 between the Lorenz case and quadratic case in such a way that if you have a period 2 orbit here in the quadratic case, what you should have in the Lorenz case, in this symmetrical example, is something that you have 1 or 2 that will be mapped 2-to-1 in a period 2 orbit. So you can have a period 2 here, or 2 period 2 perhaps, but it's something that you can identify. Something that happens in the quadratic case will be occurring something similar to this in the Lorenz case, okay? Even when things are not periodic, okay? But I'm talking now only about symmetric cases, but of course, we have the classification we had for unimodal maps that's somehow valid here, but something else can happen. will happen, okay? And so, to be formal now, in our context, we'll be talking about Lorenz maps as being a one-dimensional map like this, and a contracting Lorenz map will be a C2 map that has one discontinuity like here, and these points are fixed, and the derivative is greater than 0, and the derivative is 0 in the discontinuity, okay? The limit of the derivative is 0 in this point. And so now we'll begin to work with this kind of object, and firstly, we define the renormalization intervals for Lorenz maps as being maps that as being intervals that you can take and observe the first return, and it's conjugated to a Lorenz map. So what happens here is that you can you can have perhaps here one different iterate for f and here, but you will have by definition two periodic points in the extremities of the interval. Okay? So when you define the renormalization interval, so like here, I will take this interval as being my renormalization interval, and you can iterate the interval. So this will have this half will iterate together with a periodic object like here, and the other one to another periodic object like here. And we define a renormalization cycle as being the images of these halves of the renormalization interval that eventually return inside it, like here and here. Okay, and we can extend these cycles, these intervals of the cycle here, to the maximum interval that will be mapped into the renormalization interval. And when we consider these pullbacks and only the ones involved in the renormalization cycle, this will give us this, I call it KG, and called nice trapping region. It has the same properties as in nice intervals, but it's only it hosts the cycle of renormalization. Okay? So it's defined like this. And with this in mind, we will state the following. If we have an infinity sequence of renormalization intervals, what we have here is, as we know in the continuous case, when you take all the intersections of these renormalization intervals, you will have only the critical point as the limit. But this will not necessarily happen in the other places of this intersection. Perhaps you can shrink, but not to a point. It can shrink to something that will not, perhaps will host a wandering interval. We are keeping this in mind. So what we prove is that indeed we have an attractor set here, lambda, that is inside this infinity intersection, okay? And this is our solenoid. And this set is a Cantor set, minimal, and indeed, for a residual set of the interval, the omega set will give this lambda, okay? So this is one of the kinds of, it's a little bit different. Of course, we knew something like this should happen because it happens in the unimodal case, but something else can be occurring. So this is a concept a little bit broader than the other one. So this happens in the case of you having infinitely many renormalizations, okay? But this renormalization process, perhaps it will stop at some time, and if it stops, what can you see at this point? In the case you have a finite number of renormalizations, look to the last level, and possibly you will see something like this. Okay, if you look to the restriction between the two critical values, and you see a gap map like this here. In this case, what we have is that this is semi-conjugated to a rotation. Okay, and we use a little bit the kind of definition that was introduced by Tressé and Gambodot because of Newhouse-Pallistack generalization of endomorphisms so for rotations and to the idea of rational. And here in this context, what we have finally is that we have this semi-conjugated to a rotation. That can be a rational rotation, and in this case, you have a periodic attracting orbit, or it can be one or two. Okay, it can have two different periodic orbits, or it would be a rational rotation. In this case, it can be conjugated to a rational rotation. When it happens is when that gap disappears, contracts to a point. Okay? In the other case, when it's semi-conjugated but not conjugated, that gap do exist. It's non-trivial, and indeed it's like it is a wandering interval inside your dynamics. So in this way, you can already consider that you have to consider dealing with wandering intervals when you are considering Lorenz maps. So we say that in this case, we have a cherry attractor. When you have the rational rotation, it will give us an attractor that is a Cantor set, if it's not the case of the gap disappears. And when you have a cherry attractor, then you don't have a periodic attractor, and there is a neighborhood of C, of the critical point, in which neighborhood everybody will eventually come close to the critical point. Okay, C will be in the omega set of all the points X in the neighborhood of the critical point. This is characteristic of cherry maps. So by now we understand what happens when we have infinitely many times renormalizable Lorenz maps, infinitely many times with a gap map, but something else can occur because perhaps you do not have a gap map in the last renormalization. So in what else happens, what we finally have is this theorem. For non-flat contraction Lorenz, if you do not have any periodic attractor nor weak repeller, there will be a compact set lambda, transitive invariant, with a residual base in the whole interval of one of these types, cherry, solenoid, as we described, or perhaps a chaotic attractor. Okay? That can be a cycle of intervals, or perhaps a Cantor set. In this case, you will have wandering intervals. Perhaps these do not exist. Perhaps we can prove later that this kind of object do not exist, but at least at this point, this is the classification we have in this case. Okay? Remembering we are considering contraction Lorenz maps as being C2. But if we consider them to be C3 and negative Schwarzian derivative, then two facts we have. Fact one is the following: is Singer theorem for Lorenz maps. you can have one or you can have two periodic points because it's limited by a number related to the critical points, as in a single theorem. The discontinuity gives you possibility of having more than one. You can have two, but at most two. And the second fact is the following. If you have one periodic attractor, you can prove that if this does not attract everything, then there should be another periodic attractor that will attract the rest of your set, of your interval. Okay? So if you have one periodic attractor, then you have to have another periodic attractor or nothing else. So this is in the negative Schwarzian context, and so we can state this like here. Okay, then in this case we will have one topological attractor, only one topological attractor. That would be a cherry, a solenoid, a chaotic. Chaotic can be a cycle of intervals or a Cantor set with a wandering interval, except everything will be only one and transitive, except in this case that can be one periodic or two periodic. Of course, this here, each part, them together, this one will not be transitive because you have two different pieces here. Okay, so this is the classification we can have for when we have negative Schwarzian derivative. Of course, we have to go to search for the kind of tools because we do not have Milnor-Thurston. So we have to have another kind of strategy to build this the possibility of the attractors. And the kind of strategy I used to get them also gave me the possibility of having this following result that is a kind of spectral decomposition for this kind of maps. So if you have a contracting Lorenz map, so you can say about the non-wandering set is that there is a sequence of different compact sets, omega n, like this. This sequence can be infinity, and they are invariant. They are like this here, 2 by 2 disjoint, and perhaps you have some kind of remarks that you have to do in the first level or in the last level, something that you can have to take care, but you can describe completely as in the spectral decomposition theorem. Okay? And let's discuss a little bit which kind of tools we use for having this kind of classification and this result. So this is the strategy we use, what we just described. If you have a contracting Lorenz map, it can be infinitely many times renormalizable, what gives us a solenoid, or it can be finitely many times renormalizable. Then you have periodic attractor, 1 or 2, or a cherry-like, if it's semi-conjugated to a gap map. And the remaining case, you have a chaotic attractor that can be a cycle of intervals or a chaotic Cantor, but perhaps this we can prove that doesn't exist. But by now we have to say that perhaps it exists. So what's really the strategy to prove this all? We consider, first we consider C2 maps without weak repellers. In such a way you can use Mayer's theorem. And we have that to any given neighborhood here, you can modify your function and everything can come, can eventually visit this neighborhood. So it's true that the omega of almost every x in the interval contains C. Then we can observe that what's a nice set? A nice set is like this. If you have a set that has borders that never go into the interval, then you can decompose your whole interval by considering the pre-images of this set, okay? And you can throw away the set and all the pre-images, and the remaining set, we call lambda G, is the set of points that never visit G. This has Lebesgue measure 0 because of the my theorem. So when we consider nice intervals, first observation here is that first returns to nice intervals, they have to have periodic borders here, or they are accumulated by periodic points, okay? Main ingredient in our proofs will be the Home-Terval lemma as introduced by Mizurevich, and it says that if you do not have a periodic attractor, if you do not have a weak repeller, and you take an interval and you iterate a lot, it eventually will cover the critical point. For otherwise, it will be a wandering, or otherwise it will be a wandering interval. So if you say you do not have any wandering interval, when you take an interval and iterate a lot, it has to cover to contain the critical point, okay? And next step, the next observation is that if you have a non-flat map, wandering intervals, when they accumulate in the critical point, they do have to accumulate by both sides, okay? Because otherwise, if it doesn't accumulate by one side, suppose you have a wandering interval accumulating here in C, and another one, and the other iterates are accumulating in another point, distant to C here. This space here you can use to modify your function, C2, and we know that C2 maps, non-flat, they do not have wandering intervals, so this cannot happen. If you have a wandering interval, it has to accumulate by both sides, okay? So with this kind of ingredient, we will begin to play with the structure of the map, and a relevant statement is that if you do not have, if you take if in the whole interval you do not have any periodic point inside it, so and you do not have any periodic attractor that should be in the border 0 or 1, so to any given point, the omega set has to contain C. For otherwise, if you take a point, any point in the interval, you iterate a lot. If the omega set of it do not approach C, then you have a component, connected component containing C that should be a nice interval. But then, because of the former remark, you would have a periodic point inside the interval. So if you have this condition of not having periodic points inside an interval, then this has to occur. And we can, with a little bit more of computations, you can say that thinking already in renormalizations, if you do not have any periodic attractor, if you are not in a cherry map, then periodic points accumulate in C, in the critical point. It's almost the same that was said here. Okay? And so this is a fun principle that if you take any side neighborhood of the critical point, and if you do not have any periodic attractor, it's not cherry, then there will be an orbit that minimizes the period inside the this side neighborhood. You can prove this because if you take these 2 points, 2 of the same period, when this interval comes back, perhaps if this interval never covers the critical point like here, it will, at the period, it will see, Q will become again in it, and P in P. And so you will see something here, you will see an attractor, okay? So this interval has to pass by C at some time, at some period, at some iterate, like here in G. But if you do this, like here, it means G is lesser than the period of P and Q, and you have a periodic point of lesser period here inside, so it cannot occur. So that's true that there is only one periodic orbit minimizing this period inside any side neighborhood of C. So now we will consider to be working only with regular maps that are maps with orbits that visit both sides. Okay, it's it's not like something that would cross here, but it has to be. It's defined this way: FL of x greater than x. It's over here and under here, the diagonal. And under these conditions here, orbits visit both sides. Okay, if you take a point here, it will pass in the half, in the first and the half, right and left side of the interval of the critical point. So now we will take this as a permanent hypothesis of not having periodic attractor nor weak repeller, because this way it will be regular and orbits will always visit both sides. Okay? So in this construction here, I must observe that if you take 2 renormalization intervals, they cannot be linked like this here. Okay? The border of this cannot be here and the border of this like here. They cannot be also like this with borders coinciding. This can occur, okay? The 10th is only a comment. Another thing we can observe is that if you have a point that you look at the omega set of this point x, and it accumulates by the left side of the critical point here, you can prove that the alpha limit has to accumulate also by the right side. If it accumulates in one side, it has to accumulate in the other side. Because if it doesn't happen, if it accumulates away of the critical side of the critical point by this side, then you can prove this will be a wandering interval. And a wandering interval cannot be like this, okay? Because of that remark we made before. So now, what we have? If we have a point that whose omega set do not contain C, that is, the orbit of P perhaps comes here, and the closest it comes is P1, P2. Okay? We can observe the following. If we take, consider this is not in the pre-orbit of the critical point. If we take any epsilon side neighborhood of this P, this is positive measure, so Maillet theorem implies it has to visit here to any given delta around C. It has to eventually intersect this neighborhood. Okay, this can be done to any delta. So if we take L very big, we will have that it will cover the open interval going to C. like this. And the same if we take any point y in the pre-orbit of this point P. Another remark here is that if we take any point of the interval and consider the alpha set of this point, and we call gx the connected component of the complement of the set, that is, take a point x, consider the alpha limit of this set, and gx is the connected component of the complement, okay? And x between the two critical values. We have either gx is empty, that means alpha of x will accumulate in C by both sides, or this here will be a renormalization interval, according to our definition, okay? And also the border of this will be inside the alpha of x. So these are the two possibilities, having this renormalization interval here, or this collapsing to nothing, to an empty set. So this is, you can make this for anything here. And of course, you can take a periodic point and make this construction. That will be very useful, okay, in the, this will be a kind of algorithm. We will have to make the construction of the remaining possible set that could be the attractor. So if you do not have a cherry, a solenoid, or periodic attractors, in the remaining case, then you have a periodic point here, because one of those observations I made before, and such that C will be in the alpha set of this point. Okay, so this will work very well for us. So it also gives us a kind of process. If you are at a level of renormalization, you pick a point periodic here, and if you look the backwards orbits, the alpha set, if it doesn't accumulate in C, you will have a new renormalization interval inside. So with this in mind, we can analyze the remaining case. And if we have a point like this here, P, this is the picture of the hypothesis. If you have a point P such that C belongs to the alpha set of P, okay? For example, it can be a periodic point. And C doesn't belong to the omega set of P, like here, to a periodic point, I said. Then you will have the following. There will be a neighborhood of C such that all the previous orbits of any x in this neighborhood will accumulate in C. Okay? So this is the hypothesis. And the construction uses the former observation about those points that covers the half of the interval. If you do not have if you have a point P, like in the hypothesis, that do not approach C here, then if you take, suppose in this neighborhood, not everybody will have the alpha containing C. So take one of these points, like this key here. That construction gave us the possibility of building all those spaces here to any pre-orbit of this point P, okay? And as it covers, in the future, covers all this here, we can pick this point P here and see its pre-images inside these small neighborhoods of those pre-images of P. So it's an absolute, so in such a way that we have that everybody here shall be like this. The previous orbits have to contain C. Okay, so those are the main tools, and now I will just talk about the main construction here. So if we have, consider, first we have a point whose alpha limit contains the critical point, then it will contain the omega set of the map. So take a point of the omega set, like here, the non-wandering set. Take a point y here like this, the non-wandering set. And we know that if you take any neighborhood here like this ball, we know that at some iterate like G, it will have a point that returns inside it, okay, like this Z returns here inside as FGZ, because we are supposing Y is in the non-wandering set. Then, with this in mind, what we will do, consider Z and FZ here, okay? These points here, Z and FZ here. So you can iterate again FZ, it will come here, and again, and again, and again, and again. So you can extend this interval. And you have two possibilities. It can either reach the critical point like here, or not. If not, the Home-Tevel lemma will tell you have a problem. You have to have an attractor, or otherwise it has to cover the C in this way. But C was in the alpha of X. So all these black balls here are part of the pre-orbit of X. So you can have these guys here brought here to near Y, like this, okay? So you began with Y inside the non-wandering set, and you are showing it's inside the alpha of X, okay? So we have one direction that we wanted to make was this. And now consider the set of points whose alpha limits contain C. Okay, if you look the backwards orbits, they will accumulate in C. Consider this. We have constructed the fact that this set has a neighborhood of C. So there is an interval around C inside the set. If we take the connected component of it, we can observe that there are L and R with these characteristics here, okay? In such a way that we have a renormalization map, and we can construct from this this trapping region, this renormalization cycle. Okay, remark is that everybody will eventually fall into this region. So, we proved before that this statement, and as we are defining that by definition of E and then of U, we have this condition. So, to any point here, okay, to any point in U, we have this. Okay, so we are going to look for the other inclusion now. This is the case where we are not in the case of periodic, nor solenoid, nor cherry maps. It's the remaining case. So we have that to any given X in this trapping region, the alpha of X will contain the non-wandering set. And now we will say the inverse inclusion here. Okay? We have this and we have this. when we intersect with this trapping region. And to do this, is the same kind of tool we use again, under the same assumptions of the remaining case of the attractor, without any weak repeller. If we take C here, we will show this. How do you do this? So consider now Y is in the alpha set of X. Okay. V is a neighborhood inside U. This U is special, the definition of E and the cycle after that. And X here is in the alpha set, C is in the alpha set of X. Okay, so this point here, if you see the backwards orbits, they will accumulate here in C. So first of all, we can observe that inside this neighborhood, we can pick other points different to Y with this characteristic. Otherwise, it would build the home interval, etc., implying a attractor or something like that, that do not occur. So you can have several different points here inside this neighborhood, like this. With this in mind, we can take two of these points here, and okay, when we have these 2 points here, we can do the following. Both are in the pre-image of X, and we can look at this interval here, xy, x2, and we could iterate several times, and it would imply in the existence of a periodic attractor that we are not considering to exist. So we have that this eventually has to cover the critical point. So there is an iterate S such that this interval here will go directly here and cover the critical point C. Okay? So this happens like this. And again, we will have the following. We have that there will be this point here. This point here, by hypothesis, this neighborhood V is inside U. Remember that U and it is, as it was constructed, is the same way as E. Points whose alpha set do not contain the critical point. So if this is inside U, we have that the pre-orbits of it accumulate in C, like this here. So there is something inside this interval that is sent to X1. That is this one. Okay, so in this way, as we know, this interval here is mapped here in this one. You have one point here, this pink point, that will come to this place. So you have this construction, and it shows that, so you have that you took V, and it comes back to V. Okay, so this is inside the omega set, as we wanted to prove. I would, so this will easily will prove us. So we built this set here. These guys are equal, and we can show that this is. We can show now that the map restricted to the set is transitive. So this is the attractor we are looking for. And it's transitive attractor, etc., everything we expected. So I will come back to the whole picture. Oops. We can analyze a little bit and show that in this last case we can have a cycle of interval or a chaotic Cantor set, or perhaps it will not exist. But this gives a full picture of everything that happens in terms of topological attractors. But there is something extra that we get from all this construction, because in the same way we treated the critical, looking at the points X, and the way they approximate the critical points, if the interval is no longer renormalizable, we can do the same thinking. If you have another renormalization interval inside it, what you could do? You can consider this inside, this renormalization interval inside it, as being a pack, as being a critical point. And the same kind of tools you developed here for the approaching critical points, you can develop. It's a little bit tricky, and you have to do some work, but you can do the same kind of procedure to approximate this new, no longer critical point, but a new renormalization interval inside. And this is what gives us the possibility of having the spectral decomposition theorem. I only want to write the statement here is more or less the same. Just I want just point to the fact that we built those trapping regions Kn like here, a chain of nested trapping regions that are already prepared to think a little bit and to do the analysis to show that all the non-wandering set will be decomposed like this. Of course, there's a lot of things that you can think about and say about Lorenz maps, and indeed, I have tried to work in a lot of other things, like thinking about wandering intervals, or having a priori space to study distortions or things like that. When you think about what happens in terms of bifurcations for families, for Lorenz maps, the same way you think about it for unimodal maps. So, as I observed before, you can try to think about what happens, at least in symmetric case of Lorenz, related to unimodal maps. And this is the way that the parameter space of Lorenz, if you take no longer symmetric maps, but something like, consider, for example, if you take FA and minus FB, where F would be the unimodal usual one, FA would be, F lambda would be this. Okay, this is the scenario of the kind of things you have. And this, indeed, in this diagonal here, you see a cascade of bifurcations, of period doubling bifurcations. And here the two infinity point. And this will be reproduced around everything. But here, as you have periodic and the solenoid, and also the cycle of intervals, as in unimodal maps, you have other regions here where you see other kind of phenomena. Like here is a line where you have sharing maps, gap maps. Okay, this is a long story from this one. Okay, I think I'll stop here. Thank you.